You connect to a 400 kilowatt charging station, and it only pulls 90 kilowatts. Then you buy an 800 volt vehicle, connect it to an older 400 volt station, and the result is even slower. Today I'm going to explain why this happens, and more importantly, show how this knowledge can save you a lot of time and money when buying an electric car. Underneath all of this lies a single physics equation. P equals V has I, meaning power equals voltage multiplied by current. To transfer 180 kilowatts of energy to a vehicle, we have two options. Either increase the current or increase the voltage. In a 400 volt system, delivering this energy requires about 450 amps of current. When you move to 800 volts, only 225 amps are needed for the same energy. The numbers look simple, but the physics behind them determines how many minutes you will spend waiting at the charging station. If we say that an 800 volt vehicle charges twice as fast as a 400 volt vehicle, that is not actually correct in practice. It's a formula that works on paper but is blocked in the real world by three different walls. The first is battery chemistry. The rate at which a cell can accept lithium ions, known as the C rate, is a physical limit. C rate is the coefficient that shows how quickly a battery charges relative to its capacity. A 1C charge rate means the battery fully charges in exactly 1 hour. The second is temperature. The BMS, or battery management system, reduces power when the battery starts overheating. The third is the charging station hardware. If the physical capacity of the station is lower than the vehicle's potential, the charging speed is limited there. Here it's important to emphasize a critical distinction. Peak power and average power are not the same thing. What determines charging time is not the peak value, but the average power between the 10% and 80% state of charge range. The 800 volt architecture creates its advantage by pushing this average higher. However, this advantage only appears at the right station and under the right conditions. So why do cables heat up, and why is this so important? The answer lies in Joule's law. P loss equals I equidance R. In other words, if current doubles, heat loss increases fourfold. This quadratic relationship is one of the biggest obstacles engineers face when trying to increase power in a 400 volt system. Let's talk with numbers. To carry 180 kilowatts, a 400 volt system requires 450 amps of current. And if we take that system as a reference, it produces 100% heat load. When you carry the same energy in an 800 volt system, the current drops to 225 amps, and the heat load falls to only 25%. That's a 4 times difference. This isn't just about efficiency. Faster heat means larger cooling systems, heavier cables, and shorter component life. In a 400 volt system, once cable heat becomes difficult to manage, the charger reduces power, and you keep waiting at the station. That's why understanding charging speed starts with understanding heat. Let's go deeper into this heat issue. Passive, air-cooled DC cables in practice approach their thermal limit around the 200, 200, 300 amp range. Operating continuously above that level is not sustainable in proper designs. High-power charging units targeting 150 kilowatts and above solve this by integrating liquid cooling inside the cable. Inside the cable, a glycol water mixture circulates around the copper conductor. This mixture absorbs the heat and carries it to a cooler inside the charging station. The most critical point here is the connector pins. Contact resistance at the connection point can produce tens or even hundreds of watts of localized heat as current increases. For this reason, in systems targeting 500 amp class currents and above, liquid cooling and strict temperature monitoring become practically mandatory. Cutting the current in half has a concrete physical result. The cable becomes smaller and lighter. In an 800 volt system, the cable cross-section drops roughly by half. This means around 15 to 20 kilograms less cable harness per vehicle. Thinner cables also mean more flexible packaging. Designing cable routes inside the vehicle becomes easier, and passing through tight spaces becomes possible. On the production side, using less copper also directly reduces costs to some extent. This saving also reflects directly on vehicle weight and driving range. After understanding this part, we can move to the station side. At charging stations, the bottleneck is not power, but current. To understand this, it's enough to look at CCS2. In the real world, the bottleneck is often the cable and connector side, which in many places sits around the 500 amp range. A vehicle with a 400-volt architecture would theoretically need 875 amps to draw 350 kilowatts. That is not possible with standard cables. In reality, many 400-volt vehicles at public stations can draw at most around 200 kilowatts because of cable limits. However, closed systems like Tesla, using specially cooled cables and aggressive thermal management, can push these limits and reach around 250 kilowatts, even with a 400-volt architecture. That's why under the same 500 amp limit, an 800-volt vehicle can theoretically reach higher kilowatt levels. There is also dynamic power sharing. Some stations switch to a 90 plus 90 kilowatt mode by splitting the power equally when two vehicles are connected. The 350 kilowatt station label is a theoretical maximum that only applies when a single vehicle is connected and all conditions are ideal. In everyday reality, it is often far below that. People who experience sudden slowdowns in the middle of charging often wonder, is the drop after 50% a design flaw? Absolutely not. Behind this lies the risk of lithium plating. During fast charging, lithium ions move from the cathode to the anode and settle into the graphite layers. This process is called intercalation. As the battery starts to fill, the number of empty graphite layers decreases. If lithium ions arrive at the anode faster than they can embed into the graphite structure, they begin to accumulate on the surface and turn into metallic lithium. This buildup forms needle-like structures called dendrites. These dendrites can pierce the separator, leading to short circuits and the risk of thermal runaway. To prevent this risk, the BMS proactively reduces the current. In addition, when the state of charge becomes high and the cell voltage approaches its limit, the system switches from constant current mode to constant voltage mode, which automatically reduces power. This is not a flaw. It is a safety feature designed to protect battery lifespan. At this point, there is an important distinction. What determines charging speed, voltage or chemistry? With LFP batteries, fast charging performance can vary depending on the battery pack design. Especially in cold conditions, they can enter limitation earlier. LFP also significantly increases internal resistance in cold temperatures. At 0 degrees Celsius, an LFP battery can charge slowly even in an 800-volt architecture due to chemical limits. NMC batteries, on the other hand, allow higher charging speeds because they are chemically much more suitable. If we apply this to vehicle selection, an 800-volt architecture vehicle with an LFP battery may not deliver the expected fast charging performance during winter. Preconditioning is still necessary. Voltage architecture provides a strong foundation, but battery chemistry and temperature management can sometimes be more decisive. How do 400-volt vehicles like TOG T10X or Tesla Model Y remain below 100 kilowatts when connected to a 400-kilowatt station? Because many charging operators in the market prefer 200 to 250 amp limited cables in order to optimize costs. 400 volts, 250 amps equals a maximum of 100 kilowatts. That's why. If the cable supported 500 amps, the vehicle, depending on its architecture, could potentially reach at least 200 kilowatts. The reverse scenario is also interesting. An 800-volt battery cannot be charged directly at a 400-volt station. A converter must step in between. This component that converts low voltage to high voltage is called a boost converter. There are two different approaches. For example, Porsche's solution uses a separate onboard hardware unit. This adds approximately 10 to 20 kilograms of extra weight and means carrying a piece of hardware at all times just to make use of 400-volt infrastructure. The solution used by Hyundai and Kia is completely different. Instead of adding extra hardware, the vehicle's own electric motor and inverter are used. The motor windings act like an inductor, boosting the 400 volts coming from the station to the 800 volts required by the battery. No extra weight, minimal additional cost. A brilliant solution. The quality of this boost conversion solution is important because 800-volt vehicles do not always perform well at 400-volt stations. Some 800-volt vehicles without an integrated booster can remain limited to around 50 kilowatts at a 400-volt station. Vehicles with the motor and inverter integrated solution, however, can draw up to 150 kilowatts from the same station. That's a threefold difference. In addition, Tesla V3 supercharger units output around 500 volts and are focused on 400-volt architecture. When an 800-volt vehicle connects to them, charging speed can be limited to around 100 kilowatts due to the internal boost converter limit inside the vehicle. On the same unit, where 400-volt Teslas can reach about 180 kilowatts, you may find yourself charging at around 100 kilowatts without exceeding it. That's why it's more important to evaluate compatibility scenarios rather than focusing only on the highest value listed in the catalog. Tesla stayed with a 400-volt architecture for a long time, but interpreting this as a passive decision would be incorrect. Tesla's strategy was to remain at 400 volts while pushing the current above the 500 amp range within its own supercharger network. To make this approach work requires aggressive temperature monitoring and a very strong thermal management system. However, this is also where the difference between peak power and average power becomes clear. Even if a Tesla Model Y briefly reaches its peak value, the average power between the 10% and 80% range in many scenarios remains significantly below the peak. In contrast, some 800-volt class vehicles, under the right conditions, can maintain higher averages in the same range for a longer period. Thanks to lower current, they reach thermal saturation much later. This average determines the real length of your charging stop. After that, with the Cybertruck, Tesla has also begun moving toward the 800-volt class. The benefits of 800 volts do not end at the charging station. They continue while driving as well. Current constantly flows between the battery pack and the electric motor, and inside the inverter. In a 400-volt system, this current is higher, which means higher joule losses. In an 800-volt system, thanks to lower current, you travel the same distance with less heat loss. In real-world use, this often translates into a few percentage points, roughly in the 3 to 8% range. In a good scenario, this difference can mean an additional 10 to 30 kilometers of range with the same battery. That number may look small, but if you drive tens of thousands of kilometers per year and spend time charging on long trips, this efficiency difference can accumulate into something significant. Perhaps the most important component that makes the 800-volt architecture possible and efficient is the silicon carbide metal oxide semiconductor field effect transistor. Let's not slow down by going too deep into the details here. You can learn many of those details in the inverter video on the channel. Increasing voltage also has a limit. This limit is well explained by Paschen's law. Depending on pressure and distance, air can break down at a certain voltage and create an arc, a spark. According to standards, the low voltage limit on the DC side is actually 1500 volts. That means 1000 volts is still considered low voltage, but in practice, going above 1000 volts increases the risk of arc formation according to Paschen's law. It also raises component costs in a nonlinear way and moves away from the most efficient operating window of silicon carbide technology. That's why the automotive industry generally prefers the 800 to 900 volt range. For components above 1000 volts, capacitors, insulators, and connectors become much more expensive. The cost increase is not linear. It rises on a much steeper curve. Therefore, in automotive applications, the 800 to 900 volt class is often chosen as the best balance between efficiency and cost. It stays within physical safety limits while also operating in the most efficient range of silicon carbide technology. It is true that the Tesla Semi uses around 1000 volts, but that vehicle is produced under special conditions and with a higher tolerance for cost. Some people may not know the Tesla Semi. It is the fully electric heavy-duty truck developed by Tesla. There is also another factor. At high altitudes, as elevation increases, air pressure drops, and the risk of electrical arcing can increase even at lower voltages. So is higher voltage more dangerous? The direct answer is no, but it does require more careful engineering. As voltage increases, insulation requirements also increase. That means the safety distances you must leave in the design become larger. To manage this risk, 800-volt systems use higher insulation classes and larger creepage distances. meaning longer surface leakage paths. In addition, pyrotechnic fuses are added, and special corona-resistant wire enamels become necessary. As a result, we can say that a well-designed 800-volt system is not more dangerous than a well-designed 400-volt system. Moving to an 800-volt architecture saves cable and copper, but that saving is paid for elsewhere. Silicon carbide chips are significantly more expensive than traditional silicon components. Advanced BMS software, higher voltage-tolerant protection components, and additional insulation materials also add to the cost. Today, producing an 800-volt vehicle is roughly 10 to 20% more expensive than a 400-volt one. But this gap is shrinking. As mass production increases, costs fall, and design experience improves. The critical distinction here is not the cost of a single component, but the total system cost. When you look at the whole picture, 800 volts should not be seen simply as expensive, but fast. It should be evaluated as a balance between cost and efficiency, and that balance is shifting more in favor of 800 volts every year. Today, most vehicles on the market still use 400-volt architecture. Models like the TOG T10X, Volkswagen ID.4, Tesla Model Y, and Volvo's mainstream models fall into this category. Meanwhile, cars such as the Porsche Taycan, Hyundai Ioniq 5 and 6, and Kia EV6 belong to the 800-volt group. When evaluating a vehicle for daily use, instead of asking only, does it have 800 volts, it is much more accurate to ask, on which infrastructure and for how long can it maintain what average charging power? For those who mainly drive in the city, I'll give a clear answer. 400 volts is enough. If most of your charging happens at home or at work, there is no practical difference between 400 volts and 800 volts during slow charging. Both charge at the same speed. For people who frequently drive long distances, the situation is different. For example, on a route like Istanbul to Ankara, the charging time from 10% to 80% can be noticeably better in 800-volt class vehicles when using a good station and at the right temperature. If you drive at least 300 kilometers on the highway every week, this can add up to roughly 4 working days per year in time savings. In cold climates, 800 volts is also advantageous because efficiency loss at low temperatures is more controlled. As a practical approach, if your budget allows it, and you often travel long distances, 800 volts is a major comfort advantage. But if you only drive in the city, that price difference may not be worth it. The decision ultimately comes down to your usage habits. The 400-volt architecture is not disappearing, but it is slowly shrinking in the premium segment, and around 2027, this shift is expected to become much more visible. Two things are accelerating this change: the spread of the megawatt charging system and the standardization process. The megawatt charging system targets charging powers above 1 megawatts for commercial vehicles. And at that power level, a 400-volt architecture is completely out of the picture. The investment direction of major operators in Turkey is also toward 800 volts and above. By around 2027, investments in 800-volt compatible charging stations are expected to accelerate. Within this context, there is a concrete note for 400-volt vehicles. If you want to sell the car on the second-hand market between 2027 and 2030, there is a possibility that buyers may perceive it as having outdated charging technology. It is worth considering this perspective when making a purchase decision. My final practical advice is this: when choosing a vehicle, don't look only at the peak kilowatt value. Carefully evaluate the average power between 10% and 80%, the voltage compatibility of the stations on the routes you frequently use, and the vehicle's conversion capability at 400-volt stations. Thank you very much for watching and for your support. Take care.